So I did not record it later. Uriah and those guys will want this. So let's take a look then at what we got for the week. Turn this off behind me because nobody's here. So if you take a look, current work. This is the new unit, so you'll need to get that out and print that out if you have not done so already. Hopefully yesterday you watched How Stuff Works Water. We are going to answer the second page of that, which is actually the first page of the new unit. And then, so that's water notes. That's what we've got done going on today, and the solution notes. And then we'll sign the solubility graph. So we'll go over a few questions on that. Since there is nobody here on red days, we will have to change the laboratory for this class to make it on Friday, which means we will discuss molarity and stuff tomorrow, and then dilutions on Thursday. So we have to do a little bit of rearrangement there. Shouldn't be a big deal though. Who comes in on Friday?
I do.
All right. That's the big group, Emma and Claudia, and isn't there like three other people?
Yeah,
I come in.
Yeah.
I come in too.
Cool. So that'll give us a lot more choice of who we well, maybe not choice isn't the right word, but at least a lot more people to break off into groups with. So that's good. If you want, you should read that lab for Friday. If you weren't in here last semester, when we did laboratories or whatnot, it can get kind of hectic if you did not read the lab before, you know. So it's kind of one of those things. Leo, do you have a question, or were you just saying I'm gonna be here Friday?
No, I was just saying I was gonna be here, and I forgot to put my hand down.
No worries. All right. So those of you that were worried about this right here, this doesn't have to be turned in with the work or whatnot. That's fine. All I wanted was the How Stuff Works. And Leo, how many times did you say water?
Yeah, no, I didn't count that. It got annoying.
Yeah, I'm sure if you even started, like, you would get up to 50 within the first 5 minutes, and you'd be like, "This, I'm done."
I got to like 12, and I was like, okay, no, I'm not doing this. This is annoying.
Yeah, right. All right. So if we take a look, what is a dipole? So what does di mean?
2.
So dipole basically means two poles. And what does that mean? Well, it means two regions of charge. How does water's dipole molecular structure affect its properties? Causes it to attract to itself and others. Right? We take a look. There's an overall pull in this direction for the electrons. So that that gives us that whole thing there. There's an overall pull in one direction for the electrons. And that gives us that, what do we call it? That dipole that we're talking about. And those two regions. That makes this up here partially negative, and each of these down here partially positive. And we've shown you how, with the water molecule being able to do these things, that it can sit there and even pull apart or go through the process of solvation to an ionic compound. Why is water essential to life on Earth? This is a fun one. Why is water essential to life on Earth?
Because chemical reactions occur in water.
Chemical reactions can occur in water. Good. What else?
It's a universal solvent.
Universal solvent, good.
Because you can move around in it, it allows like small organisms to absorb things better because they could just move around and have things wash up on them.
Who's that?
Leo?
Leo. It's good. All of those are great answers. Water is essential for life because it allows for reactions to occur easier. Because the particles can move. Why do scientists credit water for allowing life to form? Without that, what is the term for where life began? What's the prominent theory? What do we call it? The
It
primordial.
was like soup, right? Primordial soup, right?
Yeah. And so we have these particles dissolved in it, and these particles are able to freely move and orientate and come into contact with each other. If they were only like two solids sitting across the room, they wouldn't be able to do that, right? They would not be able to do that. The other thing that you could have mentioned as well is that, well, I mean, living things use water to transport chemicals throughout their cells. Even the majority of cytoplasm is water, right? So that ability to move that throughout your cells, that's key right there. That's key to it. I think Emma said that water is the universal solvent. While there's plenty of water around, only a small amount of water is fresh water. Water is the blank compound. Is a what?
Polar.
Polar is probably the best word, meaning it has what?
A positive and negative end, or partial positive.
We spell positive. Negative has an A, right? Or is it I? Negative, I think it's an A. Negative and positive. Is that right?
Yeah.
And if we take a look, this is very similar to the drawing I made up there. We have a large electronegative atom right here. That's going to pull those electrons closer to it, which is going to have an unshared feeling. Even though they're shared, they're not shared evenly. That makes that negative charge up there and these positive charges down here. This allows water to both to attract both positive and negative ions of an ionic compound. Ionic crystals like salt will dissolve easily in water because the polar water molecules tear the ions apart. Lisa, you're tearing me apart. The force between water molecules is called blank bonding. Anybody?
Hydrogen.
Hydrogen.
Hydrogen, very good. Hydrogen bonding. This allows water molecules to attract to one another, giving water a high, anybody?
Surface.
Surface tension. And last but not least, this is probably the only one that I would think that you might not be able to get if you tried this before before we had today's discussion. Does anybody look it up or know it?
Would it be like non-polar compounds like soap and stuff?
Yep. Soap and detergents. Soap is different than detergents. Or you could say what we call surfactants. Surfactant. Bada bing, bada boom. That's the gist of it. That's water. Cool. So as always, I don't give like vocabulary quizzes like they would in 6th, 7th, 8th grade. But as I talk, you're going to need to know these, right? Otherwise, you're going to get confused about the math that we do with this And, you know, also multiple choice questions on the final, like the final test of the unit, which is kind of far away. They'll pop in and out of there as well. So please make sure that you do get these down. Some of these you might already know. So a solution, we learned that over the summer. A solution is a homogeneous mixture. A lot of times, what do you think? They contain a what and a what?
A solute and a solvent.
A solute and a solvent. What is a solute?
The item that's dissolved in the solvent.
Yeah. Scientists like to use this though. They say lesser number of moles in the solution. But a lot of times it is what we can consider, it is the dissolved stuff most of the time. And solvent then, what do you think scientists would say?
Greater number of moles.
Right, greater number of moles. And it does the dissolve. Solvation. Right, precipitation, solvation, evaporation. What do you think solvation is?
The
Is it the process of like dissolving?
You got it. The process. Scientists love processes. Solvation is the process of dissolving. Right? We're just doing this based on words that we've heard before. Hopefully this isn't beyond anybody's wheelhouse at this point. Electrolyte. I know at least one of you has heard the term electrolyte. It doesn't mean you know it, but where did you hear it from?
Gatorade.
Gatorade. Why is Gatorade called an electrolyte? Gatorade used to have the best commercial. What is that, Emma?
Doesn't it give you energy?
Gives you energy, right? But that's just because it's a thirst aid. That's the energy part. Gatorade is thirst aid for that deep down body thirst, right? Thirst aid, that's the sugar. That's what gives you the energy. That's not the electrolyte. Sugar's not an electrolyte.
Isn't electrolyte like something that's dissolved in water, like easily dissolved, or?
Sugar can be dissolved in water, but it's not an electrolyte. Good. So we've heard this, but we have no clue of what it actually means. That means we have something to learn, which is good. That's cool. So an electrolyte, what does your body do when you sport?
Burns calories.
Burns calories, good. Another thing it does?
Builds muscle.
Builds muscle, okay. What else? What else? Something that Gatorade can help you with. What else is your body doing when you're exercising or sporting?
Sweating.
Sweating. And what does sweat taste like?
Cheese.
What did you say? Cheese?
Salt.
Did he say cheese? You might have something on you, like some type of mold or something, if your sweat tastes like cheese. It's salt. That is another part of the thirst aid. Dissolved ionic compounds. Ionic compounds are salts. Our body uses certain ionic compounds that we have come to say that this is salt. The main one is sodium chloride. Another one is potassium. Our body also needs potassium. So electrolytes are dissolved ionic compounds that then allow the solution to conduct electricity. That's why they're called electrolytes. So the sugar, it is dissolved in there, but it is not an ionic compound. So sugar water will not conduct electricity readily. It does not do a good job of conducting electricity. But these added salts, they break apart, right? What do we call that when they break apart? Does anybody remember? Call it solvation. But another term is dissociation. Dissociation. I'm not sure how to pronounce that or to spell that. I think maybe two S there. Dissociation. When they break apart, that means that there are electrons there. So I can pump electrons into this solution, and this will gain electrons, and this will lose electrons and then gain electrons again. And it'll make like kind of an alternating path. If this gains electrons, this can come by and take it again if it lost them. And that allows the electrons to go through the water. Now, pure water does not readily conduct electricity. Let's go over what these solutions are then. Real quick, I will show you this solution right here. That is an unsaturated solution. What does that mean, unsaturated? That means it has less than the maximum that it could hold. What does that mean, less than the maximum? That's anything from a small amount to right below the amount that it could hold. If you look at an unsaturated solution, you should not see any particles floating on the bottom. Most solutions that you deal with are unsaturated. If you have to shake something, usually it's because something's not soluble or it would be saturated. This is a saturated solution, and I know this is hard to see, and I'm going to try to make it better by zooming in on different parts of it. But these digital cameras are not as good as my old whatever technology camera. You can't hook that one up to the internet. So if we take a look here, you should be able to see right at the bottom of this, there is this powder. Is this better? I don't know. But you can see that that powder moves around down there at the bottom, and then it resettles.
Is
So
that
that-
because there's more solute in it? Is that why there's powders sometimes
Yep.
settling at the bottom?
So that means that that has dissolved. The actual solution has the maximum amount dissolved in it that could dissolve. The other, the part down at the bottom, just can't dissolve because it's reached its solubility point. The last kind is supersaturated. So this does not have any at the bottom. It looks the same as the unsaturated solution. But if we disturb this solution, see if I can disturb it just barely. There we go. Barely disturbed it. Take a look at what happens. The solution has solidified. And it's crystallized now. Pretty crazy. That is how rock candy could be made. If you were here to feel this, it would feel very warm to you. And that brings up the question, how do I get that stuff out then? Would I just scrape it out? What's something I could do to this? It feels very warm to my hands because it went from liquid to solid. What can I do to this?
Could you
Can
heat
you
it?
freeze it?
Yeah, if I put that heat back in, that's a reversible process, right? That is what we call a physical process or a physical change. If I put that heat back in, I will get this back to a liquid. You might have seen this before in the form of this. How many of you are winter sports fans? You ever seen one of these before? I didn't realize you guys could see that focus thing. Sorry about that. Anybody ever?
Is this like squeeze it and you get the heat come out and stuff like that?
Yeah, right. If we make this little metal thing down here, that is our catalyst for this. If we bend it, boom, the whole thing starts to crystallize. And then I could put this in my pocket and it would feel hot and warm for probably about maybe 50 minutes to an hour. So if I had multiple of these, I could keep myself warm while shoveling or skiing or something like that. And take a look. It tells you how to activate it, but look at the recharge process. Submerge the heat pack into boiling water. Boil for 10 to 15 minutes or until it becomes clear. All right, so there we are, adding heat to it. That's our idea. That's the way.
What would happen if you microwaved it?
What has that metal in there? So I'm
That's cool.
sure that you would get some bad things happening as the metal gains electrons, and then you have the photoelectric effect, and it could spark, and it could possibly cause that to bust. You know, all of these different things. I'm not sure. Not suitable for babies though. That's funny. It actually tells you how to make it. Sodium acetate, food grade, and water. We use laboratory grade, but yeah. All right, so what is this solution right here? Saturated, unsaturated, or supersaturated?
Would that be unsaturated?
Unsaturated. This guy right here.
Saturated?
Saturated. Again, this is holding the maximum amount. You can see there's some on the bottom. And then last one is super saturated. And that
So
is a very special case. They've heated that up to get all of that to dissolve somehow. And then they've cooled it back down so that it's holding more in solution than should be theoretically possible.
Wait, Mr. Jackson, I have a question.
Yeah.
A saturated solution, so basically it's holding in the maximum amount of dissolved stuff, so that's why the rest has basically kind of formed at the bottom. Is that why?
Yep.
Okay, thank you.
So this is up from the minimum it could have, possibly up to the maximum, or just under it. This is at the maximum, and this is over the maximum. Whenever I say this, I'm talking about the amount of particles dissolved. Cool. Let's talk about, let's finish up. List 3 things that you could increase the rate of solution of a solid. So let's change this word to solvation. So increase the rate at which something dissolves. Increase the rate at which a solid dissolves. What could we do?
Could we like heat it up?
Heating it up. What's that going to do?
Wouldn't that increase the solvation rate, like causing like more particles to dissolve?
But how?
Would it make the particles move more?
Yeah,
Wouldn't make it become a liquid,
particles
right? Because
move faster, thus dissolve faster. There's two more things we could do. You guys have never been to London and had tea or had tea here in America? What do you do if you want to make it sweeter?
you add sugar.
Yes, that's true.
You
Now,
can stir it.
how do we get it to dissolve faster? We stir it, agitate it. What does that do?
Makes the particles move faster, causing it to dissolve faster.
They do move faster, but it does something else as well. It increases the surface area. Right? Because if it's just sitting on the bottom, the only water molecules that are getting to it are right around it. If we stir it up, then we put it everywhere. One last thing. You guys have never had tea with the queen? How does she take her sugar? If you're having tea with some, and it's a nice event, what
Is
state?
it like when it's cubed?
It's in a cube, right? So what would that do? If the sugar is in the cubed form, is it going to dissolve faster or slower?
Because of like more volume of it.
As the cube, more volume than what you can make the sugar? You want to crush it. You want to crush the particles. Crush large particles and basically make them smaller. Haven't you guys been to the bad part of being a kid when you have to make the Kool-Aid, but you're at grandma's house and the sugar is like one big rock? How long does it take for that thing to dissolve? Forever. But it is just so fancy to have that cube sugar, isn't it? How many cubes would you need? I'll have 2 cubes.
Isn't cube sugar like super fine though? So when it would like dissolve faster because
It's not
it's
actually.
not.
Somebody may have taken them from me. I have them, good. Now the question is going to be, is this camera good enough for us to see the properties of solvation and stuff? And that I don't know. So here is a sugar cube in water. So the problem is the camera, I should be able to zoom in on this and you actually see that the granules of these are actually the same size as granulated sugar. Powdered sugar or confectioner sugar is not this big, but unfortunately, this camera is just not good enough, I don't think. With an actual non-digital camera, it probably looks even worse for you guys, unfortunately. But with a non-digital camera, then you could actually see each of the little granules. But basically, it looks just like granulated sugar, like what you would put in cookies or in Kool-Aid and stuff like that. It looks the same as that. It's just been kind of crammed together. And that process of salvation is going on in this one. And you can see if we just let it sit there, it'll take a little bit longer. Let's answer number 11 while that's happening. How do you increase the solubility of a gas in a liquid? You can actually see kind of the water molecules right here up in this area. You can see them kind of pulling those sugar particles apart. Anybody, gas in a liquid, how could we change it? Think about your gas laws.
Increasing the temperature of the gas?
If we increase the temperature of the gas, what's going to happen to the gas particles?
They will move faster.
They will move faster. Do you think that that would keep them trapped in the water or in the liquid better?
Wait, no, never mind. Never mind. So would you do the opposite? Would you actually decrease the temperature?
Yeah. In the summertime, actually, if it's too warm out, lakes and streams will actually lose their dissolved oxygen because it's so hot. The oxygen will basically come out of solution. This is also why if you open a soda that is warmer, it will go more than a cooler soda with just might go. So decreasing the temperature. What's the other way? Nobody? Take a look at this. Did not dissolve at all in this solution. Put that to the side and somebody can tell me what else we can do to increase the solubility of a gas. We got temperature. What's the other things in our gas laws that we deal with?
Pressure? Decrease the pressure maybe?
If we have a solution, let's say that solution is soda, and we want to make it more carbonated. If we increase the pressure up here, if we increase the pressure on the surface, well then, it cannot escape because it's being pushed back into solution if we increase the pressure on the surface. Nobody has a soda stream at home?
I do.
Where were you on that one?
I don't know. I must have missed it. I don't know.
Take a look. Don't do this at home with your
No,
soda stream.
and I just got this brilliant idea to make sparkling wine using a soda stream machine and Boucher de Nouveau. Don't worry, it's not for me. It's not for me. It's for my dad.
Okay. Sorry.
Almost there.
My parents, not my parents, my dad and my sister did this
Okay.
once. So I already know where this is going.
Are you serious?
Yeah, they try to make sparkling wine. And they
Had it on
blew
video.
up the
So
kitchen
that
with
one.
wine.
Okay, now for the part we've all been waiting for.
Go, Noah.
I'm afraid this
No, just keep holding it. No,
it's going to explode.
it's okay. It's
Yeah, okay, that's good. Oh,
Holy shit!
oh, oh my god!
That's crazy, right? Poor Noah had to clean up a big mess, I bet. I wonder if he got any over his awesome shirt. Leo, was that you that said that your brother or your sister and dad did this?
Yeah, my dad and my sister did that once, and it based that happened. Yeah.
That happened. So it is real. That's funny. I wonder if it's because of the alcohol. It can't hold on to the carbonation as well. Because if we take a look, I showed you these two. Oh, come on, where's the visualizer? No, it's playing hide and seek from the visualizer. I don't know why it does this sometimes. It doesn't like the visualizer. If we take a look at these two things, this was water, where we see that the sugar is basically dissolved. This is alcohol, where the sugar is not dissolved at all. Which is kind of interesting because both of those are polar, but the water does a much better job at pulling apart the, oh, dang it, let's got this on there. How did we turn that on there? Sorry about that. Why does it even though it's polar, water does a definitely better job of pulling that off than the alcohol does. So that brings us to miscible and immiscible. And what is meant by the phrase likes dissolve likes? Well, let's take water and alcohol. Let's just take ethanol. What's similar about these two compounds? They're both going to have what?
Aren't they both polar?
They're both polar. They actually both would have hydrogen bonding occurring as well. But they're definitely both polar. And polar substances, like water and alcohol, I don't know if you guys know, maybe Leo's sister and his dad know, but they have these drinks with they take fruit and fruit juices, which is mainly water, and they mix it with like rum, and like a daiquiri or something. And these are both polar substances, so they will mix. I'm going to go ahead and say they will dissolve / mix. And they will do this with other polar substances. I'm glad that was alcohol and not water that spilled on the thing. Otherwise, that wouldn't be dry yet. So other polar substances. Well, non-polar substances like fats and oils, right? They will dissolve or mix with other non-polar substances. Is anybody out there? Anybody like hot wings? Any hot wing eaters out there? No. No hot wing eaters at all. You guys never watch Hot Ones, where the celebrities
I
eat.
have seen it. I have seen that.
You have seen that, but you don't like hot wings?
They're okay.
They're okay.
I just don't like what hot, spicy food does to my body.
Yeah, what does it do?
Um, um,
Anybody
Yeah,
ever had Joella's fire in the hole?
um, uh, it ruins the bathroom. That's what it
You
does.
don't have to answer if you don't want to. Gabe, I took you for a hot wing liker. I think your brother did.
I guarantee you he does not like hot wings.
He does not. Huh.
No, he does not like anything that has any like ounce of flavor in it.
Oh my gosh. Wow. I thought he would be different than that.
Nope.
Not one hot
Like
wing.
chicken nuggets, like he always orders them like just like the normal ones.
Yeah.
And then like hamburgers, he always asks for them plain. So whenever we go to like McDonald's, he's like, "Let me get a plain hamburger," and they're like, "What do you want on it?" And he's like, "Nothing."
Oh. It seems like it'd be so dry. Make your throat like, ugh.
Yeah, it is.
And no hot wing eaters. Has anybody ever seen somebody eat hot wings?
Yes.
Yes. All right. Here we go. Who is that? Emma? All right. Describe to me. They come with hot wings whenever they bring it out to your table. What else? What do people eat with hot wings? What does it come with?
Oh, blue cheese.
Blue cheese. Who said that?
Ranch is better. What is wrong with you?
Who said blue
No,
cheese?
I'm not saying blue cheese is good. That's just what they give people sometimes.
Oh, okay.
Who's
I thought
saying
you were
that?
crazy for a
Just
second.
saying blue cheese. Dang it. Don't even want to tell me who said it. Ranch. Ranch is
Oh,
better.
I said it. Sorry.
Who's I? Gavin.
Gavin.
Okay. Okay, good. And I assume that that was Leo hating on blue cheese and loving ranch.
Yeah, basically.
Emma, are you a blue cheese or ranch favorite?
100% ranch.
Ranch. What else? What else comes with it? What like BW3s? If you're sitting there looking at a table, what does this person have eating the hot wings? The serious hot wing eater here.
Celery, right?
Milk.
Celery. What did you say, Gavin?
Wait, does milk do stuff right?
Milk. Okay. The big serious hot wing eater at BW3s with a glass of milk next to him.
They have something with like lime or lemon, right?
Maybe.
I don't know.
Come on. What is people go out and have wings and watch football? They don't have a glass of milk. What do they have?
Probably beer.
Beer.
Probably beer. There we go. So beer, hot wings, blue cheese, ranch, celery, maybe carrots. These are all the things. So on the hot wing, there is an ingredient known as I'm going to spell this very wrong. Capsaicin. Might be an E somewhere in there. This capsaicin is what the pepper plant created many moons ago to prevent creatures from eating its fruit. Basically, and that capsaicin is what is hot. It is non-polar. That capsaicin is put into the hot wing sauce, usually mixed with butter, which is non-polar. And that is on the fat of the wing. The skin has a lot of fat in it, and that is non-polar. So all of those things are going to mix. This means they have the ability, miscible, if they're miscible, they have the ability to mix. What do you think immiscible means then?
The inability to mix,
Yeah,
not able
Not able to mix. Like oil and vinegar, right? A salad dressing, you always have to shake up because it's not mixed well. Alcohol and water, like the daiquiris we talked about earlier, or these butter fats, all of these non-polar, these saturated fats. Now, a real hot wing eater will eat the hot wing. Some people don't like hot wings, they like ranch wings. Yeah, right. Emma's like, yep, I like ranch wings. They take the hot wing and they dip it into the ranch and then they eat it. Right away, you're losing the capsaicin because it's actually dissolving and mixing with the ranch because the ranch is also cream, which is fat, right? And then it gets down into your stomach, which has this huge thick lining on it where, you know, it's not going to affect you until, as Leo was saying, well, fire in the hole, right? Fire in the hole is one of those ones where after you eat it, you know, you have an okay time, but then the next, you know, the next morning or whatnot, fire in the hole. It burns you twice. So that's the thing with this. As hot wings, that capsaicin, non-polar, so butter, ranch, and blue cheese mixed with it. Now beer, if you just put water, if you're just drinking water, you're going to mix that capsaicin around because the water is going to hold on to itself more. It does not have the ability to mix with this. Water would be immiscible with the capsaicin. Beer, at the top of beer, what do you see in the beer commercials? They're like, yeah, that looks like a good beer. You see the
Oh.
foam. Yeah, you see foam up there. That foam is actually the sign of surfactants. Just like soap foams up. So what beer does is it actually has those hydrogen bonds broken in it. And it can actually get rid of some of that capsaicin. It's not as effective as milk would be, or blue cheese or ranch would be, but it can get rid of some of it. So that's why beer and hot wings go so well together, is because it helps out a little bit. Anybody want to tell me about the celery and the carrots? Why are they there?
For a healthy diet.
For a healthy diet. Just to round off that vegetable you need, right? I need one more serving of vegetables before I drink all this beer and eat all these hot wings. Think about it like this. Emma may not need those for the way she eats them. But somebody that eats hot wings would need them. Because what are they going to do with them?
Does it help dissolve some of the capsaicin?
No. It's easier than that. You can use them to scoop out the ranch or blue cheese and eat that. Because if you're sitting there eating ranch or blue cheese with a spoon, you're going to look like a freak, aren't you? You would look insane. So these are basically just cream delivery systems, the celery and carrots. All right. Sorry about that. I went over a little bit, but that's what we got for today. Tomorrow, again, we will discuss molarity and the assignment that's due Sunday. If you want to take a look at that and have questions for that, by all means, you can download it. Have a great day, guys. Take care.
For the how stuff works water, we only have to turn in the first page since the second page is like notes, right?
You got it. Yep, that's true.
Okay, thanks.
You're welcome. Noah, how are you?
I'm all right.
You have a question?
Yes, I would like to see my quiz. We were going to go over the test or whatever.
I'll go over the quiz or the test. Let's take a look. Brody, do you have a question?
Yeah, but it looks like you'll be busy, so I'll ask later.
All right. Which one?
I just wanted to see what I got wrong and why.
Organic?
Yes, whatever the latest one was.
You don't even know what the topic is. That's your problem. No. Organic quiz capsule. Montgomery, right?
Yes.
That way if somebody comes in, I'm expecting a Scar. I don't know if you know Scar, but he won't be able to see your grade, I don't think. All right, here we've got one. The correct name for the compound shown below would be 1, 2, 3, 4, 5, 6, 7, 8 is the longest chain. You said 6 was the longest chain.
Oh yeah, I see. Okay.
Yeah,
That makes sense.
you
Additional
actually
chain.
you counted this as the chain. You didn't think about the longest, right?
Yeah.
Alkane is in and then 2n plus 2.
Oh,
It's like
I just
yeah, that would actually be an alkene because you have a double bond means you lose those 2 extra H's.
that makes sense. Yeah, that's
Which of the following is an incorrect name for a hydrocarbon? Benzene is a hydrocarbon. A 2,3-dimethyl-4-pentene would actually be, you would have this be 2-pentene, and then this would be 3,4. Because the ene needs to get the lowest number possible. So if you draw this out and actually name it correctly, it should have a 2 in front of the pentene.
I chose benzene.
Actually, I think it would be 1 pentene.
I guess I really wasn't thinking about it enough, but I chose benzene because there wasn't a number before it. It didn't like say where it was, but I guess it could have
Yeah.
been like
All benzene is that cyclohexane,
a
yeah, with the double bonds. We call it a phenyl group. When benzene's the ring or the branch, we call it a phenyl group. Not benzyl. That may be it. No.
Oh.
Whoa, did you have the same question twice?
Oh, and I got double the.
I didn't
Oh,
know that. I didn't know that could happen. Sorry about that.
that's unlucky.
Both of the molecules shown are represented by the formula C6H14. These two molecules are not structural isomers of butane. They're C6H14. So that would be structural isomers of hexane
Oh,
because there's 6 carbons. And that's it.
okay, thank you.
Yep, you got double punished on the benzene. How are we doing, Oscar?
Doing all right.
Doing all right.
I mean, I don't know. I've been working on. Well, this. I obviously what I've done is for now I've kind of just gone up to like 7 carbon chains because I think I want to see if I can't get any general rules down before maybe expanding my search beyond that.
Yeah.
Yeah, I was thinking maybe I'd like talk you through some of the things I'm like seeing, maybe also some stuff with regards to background information because I tried to do like some background research into it, but didn't seem like there was much out there. It was just like, basic like, oh, the more massive, the more van der Waals or London dispersion forces there are, and
That's true. We know that.
polar
Right?
it is. Yeah, and the more polar it is, the more the higher the boiling point. But beyond that, it didn't really seem to say much, if anything.
All right. But none of these are polar, right?
I mean, like some of them are. My what I've been more looking into is, well, for one thing, how double and triple bonds affect it, like alkenes and alkynes, because I didn't see anything about that. And then with regards to the polar stuff,
One
what
sec.
I've kind of done.
What's that? I'll be right back, Iskar. Sorry about this.
All right.
I do. You can always go through the back door. Sorry about that. Substitute didn't have a key or something stupid. All right. So you were saying alkenes and alkynes?
So that's, yeah, one thing I'm looking at is alkenes versus alkynes. And then a more general thing is kind of like positioning wise. Like, for
Where a
example,
substituent group is?
what?
Like where a substituent group is or something? What do you mean positioning wise?
Yeah. Well, I mean, like, for example, if, like, you know, one hept 1-ene has a different boiling point than hept 2-ene or hept 3-ene.
Okay. I see what you mean. You mean positioning of the double or triple bond.
Yeah. And in that respect, a similar thing I've been exploring with hydroxyl groups. I chose hydroxyl groups because they're polar, so I think that would have like a more pronounced effect on the positioning, but also it's not like, you know, like a carboxylic acid I think is a bit too massive, like the London dispersion forces might like obscure that a bit. So it's not necessarily a light thing, but it's lighter than the carboxylic acid, but it still has like polarity, I think. Quite
I
a
get
bit.
you too. And you have that, like we talked about, you have that whole carboxylic acid, like the double bonded O to that carbon causing electronegativity differences. With that as
Yeah.
well.
And then the kind of like final thing added onto that is like the relation, the like almost like the distance between hydroxyl groups. So like, for example, like a lot of the chemicals that I have like here have like 2 hydroxyl groups, and I'm trying to see like maybe the distance between those hydroxyl groups, how that affects boiling point, and like maybe just the overall shape and positioning. So that one is a bit more ambiguous because I found a kind of trend, but it's not exactly very, very clear. I'm still trying to find with that. And like, for example, for 1,3 heptane diol, I don't have a boiling point because I couldn't find one. But yeah, so that's kind of what I've been looking into and thinking about. And like I said, you know, I mean, like maybe this is in a sense a good thing because I'm looking into something that other people won't necessarily be looking into, but I couldn't really find too much information on, you know, boiling points. It was just the basic, you know, van der Waals and polarity. And I mean, there was virtually nothing more than that. I don't know if you are aware of more research or more information on that.
No, not at all. You couldn't find the boiling point of which substance?
1,3 heptane diol.
Is there a reason why you couldn't, or it just doesn't, nothing has
No.
it?
Maybe just like, I don't know, maybe I wasn't looking in the right place, or
Yeah.
like, or maybe like, I don't know, nobody's bothered to do the research for it. I don't know.
Well, that just seems weird that I mean, the boiling point would, and nobody's really studying these boiling points for what you were talking about. Is that what you said as well?
Yeah, I mean, like I said, you know, well, for one thing, we have to have some background into our paper, but also just to see if I could find what research there was out there. I looked into it, and I mean, like I said, maybe I just wasn't looking in the right place, but I didn't see much on boiling points. I mean, it was just the basic, polarity and van der Waals, and that's all it really talked about.
Yeah, that may
And
be,
even
that may be the background. I mean, whenever we talk about attractive forces and stuff like that, if without the hydrogen bonding and stuff like that, that's going to increase the attractiveness of those particles on each other, and that's going to make it take more energy to pull, to vaporize them, to boil them.
But I mean, I can't find anything that says for example, if the hydroxyl group is on 1 and 3 versus 2 and 3, it has, a greater or lesser impact, or.
Yeah, that's interesting, because I think that may be what you're going to have is you're going to have some stereochemistry going on there. I mean, if we take a look, I mean, the more branches and stuff like that, I'm sure it's probably going to increase the boiling point as well, right? Is that what you're finding?
I tried to look at that a bit, but it's a bit out of my mental capacity to do it for most of these things.
Yeah. I'm trying to think. I couldn't find 1,3 diol. I'm not sure why either. When you have isomers, the more branched the chain, the lower the boiling point tends to be. So the more branched the chain, the lower the boiling point tends to be. But it doesn't say more branches. But it kind of
Can you maybe send that link?
Let me go ahead and I'll share it with you, and we can see if it means anything to whether it's important enough. We can discuss it together as well. So let's take a look at this property of alkanes chemistry Libertas. I usually don't like the setup of these of this website, but let's take a look. I can put it in the chat too if you want. It's got all that bad extension garbage on there.
As long as it gets me to the place.
Yeah, right. Where you have isomers, the more branched the chain, the lower boiling point tends to be. Van der Waals dispersion forces are smaller for shorter molecules and only operate over very short distances between one molecule and its neighbor. It is more difficult for short fat molecules with lots of branching to lie close together. All right. So that's the thing. It's going to be about lying close together. If they can lie next to each other, closer together, they're going to have more interactions. Imagine it like this. If you were a logger, one of the first things that happens to a lot of the trees is they run it through that stripper, and that thing rips off all the branches. That way they can stack them on a truck, right? So if we're thinking about this, if these things need to get closer together, the long thin molecules are going to be better for them getting close together, and thus causing those temporary dipole moments where the electrons kind of get screwed up and you get, some of these partial charges, and now they're attracting each other more. If they're branched, imagine trying to, just look at a tree that's fallen that still has branches on it. It's all jacked, right? It's all so you would not be able to stack those easily together. For example, the boiling points of 3 isomers right here. And there we go. There's a trend that we're seeing. And then it gets away from boiling point.
So I guess in that sense, thinking about it, perhaps alkanes with odd numbers of carbons might work better, or might work the best with hydroxyl groups on odd numbers, because for example, if it's on like let me draw this out so I can explain my thinking here. Or perhaps no, maybe even. Yeah, so I'm thinking like, for example, if you had 1,3 butane diol, and maybe like because it has a 1,3 hydroxyl, 2 hydroxyl groups on the 1 and 3 would also be like technically equivalent to saying 2 and 4. They could maybe fit together better than, for example, 1,3 pentane diol, because those 2 hydroxyl groups are more clashing. I don't know if what I'm saying makes any sense, but I just think
pretty
kind
high
of like a
boiling
pug.
point. Yeah.
Yeah.
You're talking about stacking and this getting in the way, or are you talking about this?
Yeah, well, I mean, like for like butane diol, it won't get in the way because the 1 and the 3 hydroxyl groups are like the equivalent of saying a 2 and a 4, so it can kind of like fit together with another butane diol easier.
Oh,
But if it's a 1 and a 3 pentane diol, then that's still a 1 and a 3. That's, or a 3 and a 5, but that's still like interfering with the 3 in either case, and so it doesn't fit together as nicely. I mean, like it might still have like a higher boiling point because of van der Waals, but maybe the difference is less because maybe it's like a very small difference relatively. I don't know.
Yeah.
It's just me speculating.
No, yeah, that I think that's kind of the idea with this. So I can't find this is trimethyl 1,3 pentadiol, and that's going to have a huge amount of van der Waals or London dispersion forces because of the sheer number of carbons. But yeah, 1,3 pentadiol. I didn't think it would be hard to find the boiling points of some of these things, but it seems to be, huh?
Yeah, I mean, like I've kind of already kind of tried to restrict myself in having just one straight long chain, no like isomers, at least for now, because I don't want to overcomplicate things just yet.
Yeah, I agree. I agree. There's really no need. I mean, if you're trying to just get some type of correlation, you don't want anything that's gonna make this more difficult at all. I agree 100% with that. But I don't understand why under chemical properties they don't have. You wouldn't think it would be hard to get all of the information of the boiling point things. That should not be a difficult thing. Huh.
People, I suppose, aren't that interested in the boiling points of some of these obscure things.
Maybe, right? Here's 1,3. Here we go. 217. What did we say the other one was?
Oh, wait, what? This is pentane diol?
Yeah. So there we have 1,3 butane diol. And here we have 1,3 pentane diol. And it is actually lower.
1,3 pentane, 1, 2, 3, 4, 5. I thought I got 232 for that, but I don't know.
Were you using the Chem Spider?
I think I was. I mean, like I don't know. I kind of just like
I
wrote
get
these numbers down, and I was gonna.
Yeah. Where is the more details? Where is oh, there it is, properties. Nope. Come on. I haven't used this very much. Where did you find the boiling point? Because it just said it,
I mean,
like,
for a lot of the chemicals, it said it just right there. For some of them, I guess pentane diols.
search.
Yeah, I mean, like I used a handful of websites because some of them didn't have them for some of them.
Okay, cool. But yeah, so that is interesting. We have more. There's the boiling point, 209. That's a rough estimate, obviously. But 1,3 pentane diol, 209 boiling point, and then the 1,3 butane diol is 207. So I think one.
Yeah, so like the difference is, I
It's
mean, in that case,
small,
the
right?
difference is very little. So, and I think that's kind of why, because the butane DL or the 1,3 butane DL fits together with itself more nicely.
And what is
'Cause,
other things have just said, oh, it's just because of hydrogen bonding.
well, other things didn't say anything about it. That's
Oh.
the thing. Like, I mean, when I looked into, boiling points, the only factors that it mentioned that things tended to mention were van der Waals, which it just generally said the more massive it is, the higher the boiling point, and polarity, in the sense that the more polar it is, the higher the boiling point because it's more cohesive.
Mm-hmm.
And that's kind of what I was thinking along the lines of, the positions and the shapes, because it seems like apparently there is some stuff on there, but we found that link earlier, but there didn't seem to be as much, if anything, on talking about the specific shape and how that impacted boiling point.
Mm-hmm. Maybe there isn't much out there, like you said. Yeah. One of the papers actually did this, didn't it, or something similar? Didn't we find an example paper of one?
Yeah, we found a paper, but I think it was something else. I don't think it was
Okay.
quite this.
Cool. Boiling points are a measure of intermolecular forces, and that's that van der Waals stuff that you're talking about. Intermolecular forces increase with the polarization. Yes, the strength of intermolecular forces we're dealing with hydrogen bondings for some of these. Boiling increases with molecular weight. All of these things are known. I see you have comments on it. Weird. You couldn't find any other things that affected boiling points. That's what you're saying?
Yeah.
There may not be any. It may just actually be the intermolecular forces and how those are formed, which that could be some hard stuff. Yeah, there's a little bit more branches, decreases, if you look for organic relative strength of the four intermolecular forces. So that's the primary. As a number of
Yeah,
carbon.
so like it says like more branches decreases the boiling point, but it doesn't say 1,3 butane or 1,3 butane DL versus 1,4 butane DL.
Yeah, right.
Like that still has the same amount of.
So I think what you're saying
branches,
is that the hydrogen bonding is more effective in a 1,3 versus a 2,4, right? Is that what you're wanting to say?
Yeah, kind of. Well, I mean, like I think. Well, I mean, like maybe I'm thinking about it more just in terms of like the actual shape of the molecule than the force of the hydrogen bonding. I'd have to probably think about that a bit more.
Yeah.
But I guess in a sense, the closer the molecules, the more effective the bonding is, or the hydrogen bonding is. So.
Or like the tree stacking idea.
Yeah.
With the branches, I mean, you're trying to say that like it's almost like origami is probably not the right word, but some type of like shape that commends itself.
Puzzle pieces.
Yeah,
That's
puzzle.
kind of how I've been thinking about it.
Yeah, maybe something like that. Huh. Um, and here we have something. Spherical shaped molecules generally have relative higher boiling points. You want this site? Check right
Sure.
in.
Yeah. I mean, the main point of this, like me searching for that was, well, for one thing, to get an idea of like what people were saying, and like maybe like base my framework of thinking, because we don't talk about too much in class. And so, but also to like I said, we have to have some sort of background, and I can't just like talk about things. I have to cite them, and I don't think, as much as I'd like to believe that I think I'm pretty cool, I don't think I'm necessarily discovering, the cure for cancer, so to speak. I don't think I'm.
Yeah, I get you. But I mean, I think that that's going to help you with your like we were saying, like what your idea is. Though, I mean, if it's about the shapes and stuff like that, yeah, it might be hard to find those backgrounds.
Well, I think I was also just like using the ideas of bonding to support my idea of shapes. Like the reason why, like I keep using 1,3-butane diol just because I haven't thought of any others yet. But like, well, I'm sure it'd probably work for like hexane diol as well. But like, thinking about it, the closer they are together, the more powerful those bonds they are. So like, it does still follow like the rule of it. It's just not a factor that's considered to influence it really.
Well, the other
That
thing,
makes
I mean,
sense.
you've seen how we've seen the factors whenever you have something electronegative there, and that's exactly what that oxygen is, right? So if they're closer together, all the electrons around in that area are going to be able to be moved more and more and more, which could cause a higher frequency of London dispersion forces and those temporary dipoles. I mean, that could also factor into it as well. I'm trying to think of, I unfortunately don't know enough, I think, of what you mean by we need a background. So that may be something I need to look at over this week. Are you just talking about like background research?
Yeah, I mean, for we have to have a few sources and cite them for kind of just general discussion of like, oh, van der Waals forces because of temporary dipoles they create temporary dipoles, which increases, just why more mass increases the boiling point. And then I have to probably talk about, polarity. And then, I wanted to, because of course, polarity is a factor in what I'm talking about, but it's not the primary thing that I'm looking at. The primary thing that I'm looking at is more of structure. And so I was thinking like I might need more background specific to the structure, not just, the intermolecular forces. And that's what I was worried about.
I'm not sure. It may just. Oh, dang it. I forgot to stop the recording.